Okay, we are going to discuss once again amides. This is the structure of a generic amide molecule, a carbonyl group attached to the nitrogen. As we discussed, I think it was in video number 9 or 10, I believe it was video number 10, this nitrogen is sp2 hybridized, and these are a pair of pi electrons. And also, as we discussed in our previous videos, I think it was first mentioned in video number 8 or 9, that this carbonyl oxygen, this too is sp2 hybridized, and it has two lone pair electrons, and they are each sp2 electrons. What we want to talk about in this video is what happens if we put an amide into an acidic medium. Now remember, as we had discussed in video number 10, the amide molecule itself has some resonance stabilization. And it's not a real ideal one because you have the separation of charges, but this is permissible. So that would mean that the amide molecule itself, having some resonance stabilization, might not be particularly active. But as we saw in the previous videos, if this loses a proton to form an anion, the resulting anion is even more stabilized, so that amides can be somewhat acidic. Now, what happens if we put this amide into an acidic medium where we have a lot of protons available? And the reason we ask that is because this carbonyl oxygen, this has two lone pairs of electrons that theoretically a proton could attach to. Same thing for the nitrogen. We have this lone pair of pi electrons that a proton could attach to. And what will happen is, yes, we can put a proton on the oxygen via one of these sp2 lone electron pairs, but the proton will not attach to the nitrogen. And the reason is because of resonance. Remember, these are lone pair pi electrons, and they participate in this resonance system. If we put a proton on them, then they are no longer available for resonance. So the proton, however, can attach to the oxygen, to one of these sp2 lone electron pairs. So it would look like this. This has a positive charge now, the oxygen does. And we have this, the nitrogen with its pi electrons. That would be then the protonated form of the amide molecule. Can this protonated form, that should also be available for resonance. This has a double bond. Carbonyl group simply has a proton attached to it, gives it a positive charge. The double bond is still there. Let's take a look at possible resonance structures then for the protonated form of the amide. So we have this. With its positive charge. And we have the nitrogen with its lone pair of p orbital or pi electrons. And again, if you've watched the previous videos, you should see where we're going with this. We can imagine, well, here the carbon and the oxygen, they're sharing a pi. This puts up a pi electron. The oxygen puts up a pi electron. They're sharing them in that pi bond, as we discussed in more detail in the previous videos. Then we imagine that oxygen keeping both of those pi electrons for itself, leaving the carbon with no pi electron because the oxygen stole it. So now we have this. No more a pi bond, just a single bond. And normally, if the oxygen steals that electron, it's going to have a negative charge, but had a positive charge to begin with, so now it is neutral. The carbon lost an electron, but now these lone pair of electrons, pi electrons, can swing in and be shared with the carbon. So we can have a pi bond here, but the nitrogen is donating both of the electrons to form that bond. So it will have a positive charge. Carbon is neutral. It lost an electron. That would give it a positive charge with the electron that this oxygen stole, but then it gets another electron donated by the nitrogen, so the carbon has no charge. So the protonated amide molecule has this resonance structure, and this resonance structure here is superior. It's a better resonance system than this one. That is the amide that is not protonated. Here we have the separation of charges. Here, there is no separation of charges. We had a positive charge on this oxygen. Now it is here on the nitrogen. So instead of having a charge separation like we did here, what we have is charge dispersion. The positive charge is here. Now the positive charge is here. That's advantageous. That helps stabilize a resonance system better. Charge dispersion is always preferred over charge separation. So what this is telling us then, this better resonance system of the protonated amide means that the carbonyl oxygen can accept a proton. So an amide molecule, it can be acidic, as we saw in the previous videos. If we put it though into a real strong acid medium, it can also be basic, this carbonyl oxygen. And in fact, if you look in your textbook, you will see that there is specific types of acid catalyzed reactions of amides, and the whole situation is predicated upon this carbonyl oxygen being able to take up a proton, which it does quite readily because of this superior resonance system. Okay, that's all we want to say in this video. But again, if you've watched the previous videos now, you'll see that even for simple molecules, they can do a lot of things. The amide molecule, it can be acidic or it can be basic. And again, to try to get a feel as to why it can have these different properties, a lot of it can be explained in terms of the different resonance systems that are set up. And in fact, in the previous videos, we had pointed out that even for carboxylic acid, we need a better writing pen. A generic carboxylic acid, and again, the oxygen is sp2 hybridized. It has a lone pair of sp2 electrons, which we donate, which you show in the Lewis structure like this, that even for a carboxylic acid, this can be protonated. We discussed that, I think, in video number 9. And when it is protonated, has a positive charge, and it too has a resonance structure that looks like this. Double bond. And again, we have the charge dispersion. So, as we explained in the previous videos, this carbonyl oxygen on our carboxylic acid, because of the resonance here, this is actually more basic than the carbonyl oxygen of a typical aldehyde or ketone. However, for the amide, this has a better, the protonated form of an amide molecule has a better resonance system than the protonated form of a carboxylic acid, because even though we don't have charge separation, we have this charge dispersion. Here, this electronegative oxygen still has a positive charge on it. When we protonate the amide, the positive charge is on a nitrogen. This is less electronegative than the oxygen. So what we're trying to say here is that the resonance system of a protonated amide is better than the resonance system of a protonated carboxylic acid. So if we consider the basic properties or the basicity of carbonyl groups, then this is more basic than the carbonyl oxygen of a carboxylic acid. This is more basic than the carbonyl oxygen of a typical aldehyde or ketone, as we explained in the previous videos. And again, we can make sense of the whole system by considering the different types of resonance systems that are set up. Okay, that's all I want to say then for this video. Remember that the playlist for all the videos is at the website digital-university.org.